Hello, welcome to our Bringing the Heat webinar series. We are going to go ahead and get started. We are re-recording the first half of our webinar due to some technical difficulties, and we'll have a third panelist join us a bit later. We do look forward to audience participation. There's a Q&A chat box at the bottom of your Zoom screen. Please feel free to ask our panelists any questions that come to mind throughout the conversation. We will answer your questions directly during our planned discussion, but if we are unable to, we will review all the questions following the end of the conversation, and our panelists will generate responses and we'll get them emailed out to all attendees. And with that, Gorham is going to take over from here.
Thank you. Thank you so much, Kaylee. Quick introduction to why we're talking about this. The old AFFF had a lot of PFAS in it. You see some of it on the left there being drained from a foam concentrate tank. We are going to start using F3 or fluorine-free foams on the right. You see an example of that, and I'll play a quick little video really quick just to show you. You can kind of see how thick and viscous the orange stuff is on the left, and this new F3 foam is really low viscosity, very. A major challenge when you start using the F3 is making sure it works right and it isn't contaminated with PFAS. And this, whether you're cleaning a truck or a fixed system, you gotta get the old AFFF concentrate out of there, and also the PFAS impacted things that are sitting on the inside of pipes and so on. If you don't, you might have foam that doesn't work right, and you're trying to put out a fire and your new foam is just not working correctly. Or you think you have fluorine-free foam and you apply it in an exercise and you actually don't because you have old PFAS in there and you're now contaminating a new area. So that's why this clean out is extremely important. And today we'll be talking about not just fixed systems and fuel and vehicles and how they're different, but also what fluids you can use and what tricks you can use to get them nice and clean. So here's a quick overview of the cleanouts we've been involved with. Matt Ingram from Cornelsen is going to join us for the second half of the presentation, and he'll be talking about a lot of experiences from Germany and England with fixed systems as well as vehicles. Greg Knight, of course, is our TRS expert in this and perfluoride business manager. He's here with me, and again, we'll be sharing experiences from about 200 vehicle cleanouts, about 50 stationary system cleanouts, and then also talk about perfluoride as a water treatment agent. It also works as a flocculant and can take the nasty turbid water with PFAS in it and via flocculation make it a lot easier to polish with carbon, for instance. Quick little history of the secret sauce that we're going to be talking about, the perfluoride here. Was developed by Martin Cornelsen of Cornelsen in Germany. And they basically did a lot of remediation. And for a while, since 2001, 2007 or so, PFAS was starting to enter the conversation in the environmental field. And in 2014, they came out with a patent issued on perfluoride, which is something Greg will tell you about in the next slide, and started cleanouts with this on a commercial scale approximately 7 years ago, mostly in Germany, but now we're doing it also in North America and England, of course. And you see the TRS logo there. In 2022, TRS it came up and got an exclusive license for using perfluoride in North America, and that's using perfluoride for clean out of vehicles, fixed systems, and also water, as you saw in the previous slide. And now I'll turn it over to Greg to hopefully explain to us a little more about this perfluoride, what it is and how it helps us.
Yeah, thank you, Gorm. So perfluoride is basically a plant-based oleic acid, and how it kind of functions is it makes an ionic bond with PFAS when introduced into water that's been contaminated with PFAS. One of the things that Cornelsen encountered, during the water treatment was trying to come up with a substance that to help treat PFAS without using carbon and ion exchange, an alternative, maybe a lower cost alternative. And they set some criteria up for when they developed perfluoride. They wanted to do no additional harm to the environment. So they didn't want to create a product that was, solvent based or any type of other hazardous chemical into the environment and into the treatment process. So they came up with plant-based product based off food grade ingredients. There's some chemical enhancements made to the formula, but basically it's biodegradable, so no harm to the environment. So what it does is it comes into contact with the PFAS, and then it makes microflocks that you can actually see in the video. You will see the stirring going on. This is in a flask in the lab. And as the stirring mechanism stops, you will see the flocks form. That's PFAS and the perfluoride forming. Now in the lab, it's a very clean, process, and there's not a lot of outside influences. But you look in the photo on the right, you can see that filtered flock um, coming through, and it's visual. You can see it, and it pulls the PFAS out. So that's basically how it works. It's basically ionic bond. It's a flocculation process. And during that time that Martin was developing this, um, there was a fire brigade in Germany that had done a clean out, and then they were having a problem with PFAS. They were still getting there's sampling protocols in Germany that they had to sample month or annually for PFAS, and they discovered that they had a PFAS lingering issue from the transitions to F3. So they approached Martin with the idea to come in here and use the perfluoride to try to clean their trucks out. And lo and behold, it's very applicable technology for the transition process. It actually helps pull the PFAS off the tank walls, the piping. So it became a very, very effective tool to clean out firefighting vehicles.
Nice. Thank you so much. And it actually, when it cleans vehicles, right, it's used quite differently. It's heated and it's flushed through the systems, with attrition, as we call it, right? So we got some
Yes.
pressure cycling going on and some real rinsing and washing on the inside of these systems. I'm sure, yeah.
Yeah, because it's part of the mixing mechanism. You can't duplicate that in a truck, so you have to do it a different way. So
Yeah.
over time, Martin and the Corneliusen team have came up with a methodology of using attrition, for pumping
Yeah.
fluoride in water in a solution, basically flushing it through the trucks and back into the system and running it
Mhm.
through the rest of the piping. So looking here, this is kind of you've got the process flow on the left, and then this is a photo on the right of the actual system. They kind of mirror each other. They're kind of laid out the same way. So what we do with a typical fixed system clean out is, we drain the system of any existing fluids that are in there that you're going to clean out. We create this perfluoride solution. It's a heated water and perfluoride. That's all. No other additives, no other chemicals, coagulants. Um, so we mix that up, we get the perfluoride to dissolve into solution, and we basically create a recirculation loop between our mixing tank where the perfluoride solution is created and the system that's being cleaned. So you're flushing the perfluoride solution into the piping network. Depending on size of the network, you may break the piping into smaller sections, or basically a recirculation, like a washing machine, so to speak. So that's done for a determined amount of time. Um, After that is done, you take that spent solution. It's now not just perfluoride and water. Now it's perfluoride bonded with PFAS particles in water. So we transfer that to a sedimentation tank. And that sedimentation tank, we mix it up with a little bit more perfluoride, a small dose, mix it up, mix it thoroughly, let it settle. And then you've got a flock that is settled to the bottom of a cone-shaped tank. You see it here in the blue in the center on the photo in the diagram. So in the photo is the white tanks. So we let that settle, and then we pump that through a filter, and we capture that block, the fluoride and the PFAS in a filter. We've now removed the majority of the PFAS is now out of the solution, and now it's concentrated in a bag filter. The remaining water left in that tank is then just filtered through a higher micron bag filter, and then it's polished through carbon. And typically, we're almost done. There's no more treatment that needs to be done to that water. And with approval from sanitary sewer district or the POTW, you can send that down to the sewer. So very kind of a dual treatment process. You've got the removal of the PFAS from your system, and then you've got the removal of the PFAS from the rinsate.
Yeah.
Very unique process.
You mentioned a lot of pipes and stuff. So when you do a fire truck, you don't just clean out the foam tank. Is that right?
That is right. Yes. So you can clean the foam tank, which is kind of like the source area and comparing it to environmental work, but there is the plume, the down gradient portion. That's the piping. You need to
Yeah.
chase that as well because that's been exposed to foam. So it's
Mm.
got PFAS on it as well. So in a fire truck, for example, you clean out a triple F tank, the piping, the discharge, you've got undercarriage sprinklers. For suppression system, you're chasing everything from the proportioner all the way to the end of the piping. Some hangars, that's a large amount of piping, and you may have to break it into smaller parts. And here's a photo kind of example of the two. You've got a photo on the left. That's a
Mm.
firefighting vehicle. You open up the door. This is what you see. And on the right, you've got basically your riser system, for your fire suppression system. And it's in a building. It's typically in a control room or a basement. They basically operate on the same concept. The only difference with a fire truck, you're limited for space. So everything's compact and hidden behind walls and around under tanks and behind other apparatus. You've got hoses, hose reels. So
Mm.
the truck looks very complex, and it's a lot of it is hidden. The building's a little bit different. You can see more of it. It's more accessible, but it's basically the same concept. But you can see on the photo on the right, everything's very tight, close together. You've got a lot of valves, and you're not sure what everything does. And then the photo on the right, you can see the valving with each line. You can follow where each line goes. Pretty straightforward, but larger, for a
Yeah.
better term.
Yeah. And there's a couple of different ways these stationary systems can be, right? They can be basically be empty in the lines, or they could be full of water, or they could be full of premix, right?
Right.
Which is
Which
quite
another,
different.
yeah,
Yeah.
that's another part you have to look at. You need to do some your homework and find out what are you looking at. Do you have an open
Yeah.
system, basically empty? You got basically an open sprinkler head. All those have to be plugged and capped so you can run your perfluoride solution through there. Closed system, you've got the sprinkler heads that are heat activated. Those you don't have to remove, but you need to drain that water out before you start
Mhm.
introducing more water. The same
Yeah.
with the premix. So yeah, you've got a lot of different challenges and things that you have to manage and look at, planning.
Yeah. You said drain out. How do you drain out? Look at this pipe over on the left that bends down and comes back up, for instance. That would
Yeah,
be a challenge.
that is a challenge. You have to coordinate with your facility. Again, just looking at drawings, you can kind of get a good sense of what's happening, but the drawings typically don't reveal everything.
Mm.
Drop legs are usually indicated in the drawing, but you may not need see how bad they are and realize that 30 feet away it goes back up. Now you've got a dead leg, so to speak. You've got to
Mhm.
find ways to evacuate it. So there is some planning and coordination with the facility owner, the maintenance team, et cetera. You may have to come in and, for example, in a low spot, you may have to tap and add a valve
Mm.
to allow that to drain. Depending on the length of run, use compressed air to push fluids out. And the photo on the right is a good example of, when they put in the fire suppression systems, that's usually the first thing that goes in. Everything else gets built around it. Um,
Yeah.
so there are obstructions that you may not necessarily see on the drawings. Now you've got to address, especially if there's a drain or a sprinkler head. And in this photo on the right, there's a stainless steel pipe near the ceiling. Right there. There's a little small section. That's the fire suppression system line. Everything else is HVAC
Yeah.
or some other chemical flow lines. So electrical, regular potable water, roof drains. It just goes on and on of the
Yeah.
obstructions you're going to run into. It's
Would be
challenging.
would be easy if they just always colored them red, but that's not the case, I guess.
That's not the case. No, they're always usually typically they're kind of red in the control rooms, but somewhere along the way they stop painting them.
Yeah. All right, let's shift a little bit and talk about how we rinse or how we clean these systems. It's tempting to go, oh, these are long pipes, this is large volume. Why don't we just push water through and say we're done? Can you explain a little bit about why we don't do that?
Well, water is obviously we know is not a great remover of PFAS. It will remove PFAS, um, but with the water removal, you are looking at two things that you have to keep in mind, especially if it's a pre-mix system or a system that's been accidentally discharged. You have AFFF residue in the system, so you thinking you've got your volume calculations. I'm going to do a water rinse. Uh, you have enough containment to hold that water. You will generate foam. That's one of the things you have to be aware of. Water only, that's how it's designed. AFFF and water make foam. So as you start to add pressure and attrition, that foam is going to develop. And all of a sudden, the containment you thought was enough may not contain it all. You may have a quarter water and three quarters foam. Now you don't have enough containment. The second part of that equation is you are dealing with PFAS. It's odor free. It's not visual. You can't see it by itself. It's just not visible. So how do you know you're getting it all?
Mm.
That's $1 million question. So the nice thing using like a product like perfluoride actually helps minimize the amount of foam generated in the process. And as we said, it flocks. You can see the PFAS. So there's a visual representation that you're getting PFAS out of the system. Um, a question maybe is like, how do you know when you're done? And again, that foam generation is a good indicator of when we're done with perfluoride. As we're processing the water and flushing it and doing it, and we do multiple flushes. We don't just do one. We do anywhere from 2 to 5 flushes of a system, be either a vehicle or a system. Um, every successive flush, we see less and less of the AFFF type foam. There's a little bit of foam that's present, but that's more small cell. But the large cell foam is our good indicator. And the lab data we've collected kind of corroborates that uh,
Mm.
kind of milestone that we've completed the work based on foam generation.
Yeah. So if you do a water rinse first of a truck and the water turns clean like this, you could think that you're done, right? But we have an example with us of where we basically did a water rinse and then introduced perfluoride to see if there was anything else in the system.
And the perfluoride also acts like a soap. And I use the analogy we've used it a few times. It's like if you're washing a cookie sheet, you cook bacon on it, you've got all that grease. So you go to wash it, and with cold water, not as effective. It'll take a little extra, but you can get it clean. But with hot water, the job becomes a lot shorter. So the hot water perfluoride acting like a surfactant, not only are you seeing the foam in this photo, you're seeing a lot of rust and debris that's pulled out of the truck. So it's doing a very thorough job of removing particles and debris and PFAS and AFFF, as you can see the foaming. And you can see in this photo, if you look in the lower right-hand corner of the tank, you kind of see some of those flocks forming. A little hard to see, but they're kind of there.
Yeah, yeah, fantastic. So another visual, I know that you have other ways of checking whether, for instance, a tank is actually clean, right? When it looks clean.
It's clean.
I'll
Yeah.
show you. Yeah, we'll look at this a little bit, and you can explain,
Yeah.
please.
Yeah. So you think you fill a tank with water and you drain it and you say you're done, and then you maybe go in there and power wash it to make sure you're done. Now you've got this. You generate a lot of foam. Again, there's the water, AFFF equals foam. This is what you get. So just water is not enough. After a single rinse, you go to power wash this tank. This is what you're going to see. You're going to see a lot of that residual AFFF formulating the foam. And these tanks have baffles, a lot of these on these vehicles that are you can't see every part of the tank.
Hmm.
So a very thorough cleaning with agitation and additive is essential. Or you're going to be chasing foam for a long period of time.
And this is PFAS containing foam, right? This is not a soap you would
This is not a soap. This is AFFF. This is if you look at some of those bubbles on the side wall, they're pretty large, and
yeah,
that's typical of AFFF.
yeah. So that's a major reason why we use the perfluoride at the elevated temperatures. And so this no longer happens, right? Because all this PFAS would petition into the new foam concentrate if we
Right.
just did the water rinse. All right. I know we also have some data on treating basically the first rinse, how much is actually in the system, what is in the system after a water rinse only, and what actually is in the system after you do complete perfluoride rinsing. So I'll ask you to present that in a little bit, and just right now say hello and welcome to Matt Ingram, who was there for the original recording and therefore participates in the rest of the webinar.
Yeah, a couple of years ago, we did a demonstration for airport private client. They gave us one of their trucks to clean out, and so we decided to let's do a triple rinse, with water only, cold water, and then use perfluoride at the end to do a clean out, compare all that data. So what we did, we drained that AFFF tank out, we filled it with water, we collected a baseline sample. That's the column you see to the far left, 62,000 nanograms per liter total PFAS. Drain that water out. We did a triple rinse and filled that tank again with potable water and took a sample. That's what we got. We actually saw an increase in the total PFAS. And it was predominantly 6,2-FTS, which is a huge part of the AFFF mixture. And then we drained that out and we applied the perfluoride process. I can't remember. I think we did 3 or 4 flushes using perfluoride. We got it down to 394 nanograms per liter total PFAS. And again, 6,2-FTS was the dominant compound, but it was a lot lower concentrations. So that's a good example of, to me, it kind of the data implies that, if you do a triple rinse, I think you're just starting to scratch the surface. You're just getting started. I think triple rinse, single rinse, clearly not good enough. Triple rinse, still not good enough. You need to have more. And perfluoride adds that additive that helps pull that PFAS off the wetted surfaces.
Yeah. We have a question came in from Craig. It says, to what level of residual PFAS, what's the goal and how do you practically measure it with lab turnaround time?
Well, I mentioned earlier that we use foam generation as our indicator. That actually has corroborated well with the data. So we'll do, on a fighting vehicle, we'll do 3 to 5 flushes of perfluoride through the truck. On fixed systems, we'll do 2 to 4. That foam generation is kind of an indicator. We stop generating that large cell foam that you see with AFFF. And that's kind of our indicator. Said, okay, we're going to stop here. We'll collect our sample. And so far, that has corroborated with 99% or greater reductions in the total PFAS. So that's our best indicator that we use. We obviously corroborate with lab data, but there are no real fast turnaround times in the lab yet. So, you're always waiting, 2 weeks is kind of what we're seeing now. It's better. Post-COVID, it was horrible. We were talking months waiting for data. But 2 weeks now, I think, is reasonable. We don't keep the truck or system out of service for that duration. We just use that foam indicator to say, yeah, I think we're good. And so far, the data's backed it up. So.
Yeah. Good. Very good. Matt, maybe you have some results from the fixed systems, some of the stuff you've done in Europe.
Correct. Yeah. And they align very well, really, to what Greg's just discussed. So the initial figures here are a bit higher. And I'd suggest that's probably, we do have a wider suite in Europe. And we're measuring some of the precursors directly. So the original numbers are higher. And then the final numbers are in the same ratio, the same sort of percentage reductions. I'd like to think on that previous slide, we'd have probably got lower with more rinses of perfluoride. So I'm guessing you did a quick rinse of perfluoride after the triple rinse. But the numbers are always the same. We can hit these 99.99% reductions. And I guess it's worth saying at this point, we've run straight determinant analysis on this. We've run topper analysis. Topper tends to show us a higher percent removal. So we prefer to use our determinant suite with extension to some known precursors that are in the foams. We've done quite a bit of work with one foam manufacturer in particular and have a good insight on the ingredients list in their historic AFFF foams. Ones they're not manufacturing anymore, but a lot of the work we do is, of course, with ones that have ceased production. So having that insight was really handy to know what to look for. And we introduced Capstone B to laboratories quite some time back. We had a lab in Germany analyzing for us, and that's now become known as 6,2-FTAB. And people who are doing this work routinely will realize that 6,2-FTAB is in firefighting foams to very high concentration, and it degrades into several PFAS, but 6,2-FTS is one part of its pathway, and PFHXA, PFHXS, and others. So having that one as a known targeted compound has been good for us over the past sort of 8 years. It's roughly 5-fold the concentration of the other PFAS we often find. So our numbers look higher coming in, but this is probably the same numbers as Greg was showing. It's just some things were hidden on his side. We've got 2 examples here, broadly the same on both. And at some point we stop rinsing based on, again, we use a foam test as well. There's a documented shake test, actually, one country I've seen, where you place an amount of liquid in a bottle, you shake it like hell. If you can't get a head of foam on it at all, if you get some bubbles that break down, it's generally regarded to be about 1,000 nanograms a litre with this AFFF. So we use that as a quick ready reckoner, and then some knowledge behind that afterwards. So we'll always, when we think it's okay, we'll nearly always conduct another rinse cycle anyway. And then we'll rinse that out with fresh water, and then we'll put sample fresh water into the tank or the system or the pipeline, and we'll leave it for a period of time so it can pick up any free PFAS that are on the surface. And then we can take that sample and we can analyze it and compare it to the same test at the start of the project before we did the rinsing, after we'd removed the concentrate. We believe that best simulates the operation mode of the system, because the system carries water or foam concentrate or mix of both, and that liquid is exposed to the surfaces, so that liquid will absorb from those surfaces into that media. So by testing a sample slope media, we can simulate that use. But in Europe, we are also stuck with 5, 10, 14 days lab turnaround times.
Yeah. Good. So we've had a couple of questions started coming in on the waste we're generating. I'll start with maybe the first one. What do you do with the old PFAS concentrate you collect? I'm assuming, Patrick, who asked the question, that you mean the AFFF concentrate that's removed. And just a reminder, we don't flush that out with perfluoride, right? We initiate the process by draining and extracting all this concentrate we possibly can. And I don't know who wants to answer the question of where does it go?
Well, there's several options, but yeah, basically the AFFF concentrate has to be removed from the system before we start our work. That's the first step, and that has to be disposed off site. The options are, I'm gonna say limited, but there are a few. Landfill is one, solidification and landfill. There's destruction. There's a second, and in the U.S., there's a few other. Deep well discharge is another. Incineration, people are going away from that, and kind of DOD has banned it. There's just some questions about how effective incineration is with PFAS. Obviously, it's a forever chemical, so you're talking high temperatures. So people are going away from that, but that tends to be the options available.
So, and I know we're talking about big systems here, but as an example for a truck, and now we're talking about the waste that we're generating, an example of a truck that may have, say, 100-gallon foam tank. There's that much concentrate to dispose of, and then we rinse the whole system, the tank and the pipes and everything. We generate how much water, and what happens to that?
It varies. Depending on the size of the system. For a fixed system, you were talking into volume of water that, how big is your warehouse, how big is your hangar? But yeah, I mean, for a truck, typically what we see for rinsate, somewhere about 3,500 to 5,000 gallons per truck. So that water with perfluoride can be treated. So that does not have to go off site. That can be treated, concentrations that you can send it down the sanitary sewer with approval from the regulatory authority. So that kind of waste stream can be managed on site. As far as other waste, there's the PPE. You've got some tubing that has to be disposed of, some bag filters in the process. You've got maybe a drum or two of PPE and those kind of expendable products. And then we have the when we do the rinsate treatment, that PFAS perfluoride flock that we filter out. That's concentrated PFAS. So if you've got 10,000 gallons, or let's say 20,000 gallons, you got a frac tank of treated rinsate, you may come out with maybe 4 or 5 bags of this photo here, that filtered flock. This is what we get in the back end. So it's let that dry out, and then we just consolidate into one drum. So you're talking one drum or less, volume of less of PFAS to dispose of, concentrated PFAS. So you've got a couple of drums of that, a couple of drums of PPE, and then you've got some drums of the carbon that we use for the polish. And we're not using large amounts of carbon because we've removing the majority of the PFAS out through this process, through the rinsate treatment. That we're using 200-pound vessels, so we've got 400 pounds of carbon in the back end to dispose of, and that goes for offsite. That's landfill type.
I think Greg has a big point there as well. You mentioned draining the system. So you drain the concentrate from a fire truck, and you drain the concentrate from a building, but also in a building, if that building's charged with premix, then you have to drain that premix, and that can be thousands and thousands and thousands of gallons. And of course, we can treat that with the same process and reduce that to almost nothing, and the liquid water, treated water, can go to your drain. So that's a really big advantage of this process.
Yeah, that's the rub with the suppression systems, the fixed systems. I've got dry systems, you got wet system, premix, wet. Yeah, and it's or unplanned, contaminated system that's just water only that has found PFAS, that's found its way into it. Failed check valve, or reverse check valve during a maintenance event. Things happen. So yeah, that's another hurdle with this suppression systems.
So we heard earlier that for a fire truck, it takes maybe a week or so, from maybe you start on Monday and you're done on Thursday or Friday, right? And you move on to the next vehicle. How about the fixed systems? How long do they take to clean?
So really, that's a piece of string question, hey?
Yeah, I know it's an open question, but it came from the audience, not me.
Yeah.
Okay. Yeah, so because they can stretch through multiple floors of buildings, or even into multiple buildings, it's really only quantifiable after proper visit and analysis of it. The foam tank itself and the immediate manifold around the foam tank is going to be absolutely akin to a fire truck. It's when you need to consider the premix lines running through the building and all the nozzle heads, and are they over offices, computers, are they over chemical tanks, are they over manufacturing processes? How do I get access? How long will that take? That's when these things start taking a lot of time. It may be the building's only available for some weeks of the year, so you have to wait until those weeks come around on the calendar. But essentially, it's a completely open question. The foam tank, though, is likely to be simpler than a fire truck because it's very unlikely to have baffles in it, because it wasn't built for moving. And baffles make these fire trucks complex. So,
thank you. Airplane hangars, have we used it for heliport?
I have not seen one come across my desk anyway, but I imagine it's no different than an airplane hangar. So yeah, the systems are very similar in that respect, how they're designed, but the specifics of each system is unique to that facility or building.
Yeah. All right.
So I got asked to look at heliports on boats.
Yeah.
Yeah, completely comparable.
Yeah, I know there's tens of thousands of ships with AFFF systems on board, that's a whole different and a whole new topic. But cleaning some of those out while they're in dock anyway for maintenance may be a future application of this.
Mm.
Yeah. There's a question about perfluoride, if it also can act as a defoamer in the case of an accidental spill of AFFF.
We have not applied it that way, but it does help stamp down that foam a little bit. So
Yeah.
I think it'd be worth trying, making a solution and spraying it through like a power washer with a very wide angle, very wide sweep to try to tamp it down a little bit. I would prefer that over just water alone.
Yeah. Yeah.
But
And then
yeah,
the second part.
I don't know if UK has or Germany has attempted it, but I've never attempted it.
No, I think you need to be careful because the flocs are quite sticky. So you may end up binding that PFAS then to your surface. And then because it's a biodegradable product, as the perfluoride portion of those flocs breaks down, it will then release that PFAS. So some care would have to be taken.
First, right?
That said, we have had a client using it to do a bit of a decontamination on concrete. Because they've been pressure washing with water over and over and go. It didn't give the same results as metal and plastic surface, but it did give them a positive result.
Yeah.
Yeah, I guess containment would be the first step. And that, sprayed water to try to control it. You have to try to capture as much as possible.
Yeah. And we have another question. After the final water rinse of lines, are results close to non-detect? Sounds cheaper than purchasing a new ARF truck. And what is the typical cost to completely rinse the truck as an average?
So it's twofold. The first question, yeah, it's not close to non-detect. We can't get all of the PFAS out. I think that's impossible. I think that PFAS was designed to be persistent, and it's proven to be persistent. But we typically get 99% or better reductions, but that is based on what your starting concentrations are. So there could be as low as under 1,000 nanograms per liter or slightly over. Then as far as cost per truck, there is definitely a savings if you're doing multiple trucks. So you've got an airport and you've got a fleet of 5 ARFs. It's going to be a lot less per truck than say I'm coming out to do one truck. So I'd say the price ranges from 40K to 100K per truck, depending on location, size of the truck, etc. US dollars.
And that's an ARF truck that would cost
like
$1.5 million to buy a new one, right? 1.5 million.
Probably about 1.5 or more at this point.
Yeah. Cool. Can you confirm that perfluoride is used to remove PFAS from 3% mixed foam in fixed systems? I think that's an easy one.
Yes.
Yeah.
Right.
Yeah, that's definitely one of the AFFF concentrations, or 3%, 6%.
3 or 6.
Yeah.
Typical.
Better, right? Yeah. Very much we provide kits with perfluoride to spray on things like that, and I would say to that, it typically would not be a great application. The way the perfluoride is most effective for cleaning systems is when it's actually dissolved in water and warm at 120 Fahrenheit or 50 Celsius, and it's a little tricky process to make that perfect solution there. And I don't think there would be like a spray container or anything like that, right? Because at room temperature it's not the same.
Yeah.
You'd be fine at room temperature for that use. I mean, the reaction can happen as long as the water's not frozen. But the sticky residues would be a problem. I think you'd end up sticking your contamination to your surfaces because you wouldn't have that agitation and removal mechanism that we have when we have a controlled circulation.
Yeah. All right, and one more. Where do you keep the water with the flocculant while it takes time to dry out? Where and how are you keeping the water while it dries out? I guess that's
Oh, the filtered flock,
yeah,
probably.
yeah,
Yeah, so what we typically do is we have like a little clothesline. It's pretty primitive, but we just hang it over a 55-gallon drum and just let it drip dry. And that water that drip dries, we put it back into the system for the next batch of treatment. So it's getting put back into the system. And then once it's dry, it's transferred into a separate drum and then keep the lid on it while it's accumulating.
yeah. Are there any concerns about short or long-term impacts of the systems from the perfluoride itself? Any data on this? Essentially, Matt, you started by saying one of the three criteria for perfluoride was do no harm, right? But here's a question:
So that's a good question. And I guess a key point is we haven't discussed about the rinsing process in detail because there's quite a lot of IP in it. But one thing we do, there's a follow-up water rinse behind the perfluoride rinse each time to remove any perfluoride. The second point, we've worked with several manufacturers of wheeled fire trucks and dosing pumps, and they all agree that we're chemically compatible with their equipment. We actually decontaminate the proportion of pumps for one brand when they undertake to work on systems. The perfluoride itself will biodegrade, so if the perfluoride left behind in water in the system, it will biodegrade and it completely degrades to hydrogen, nitrogen, carbon. But a key point here is that water cannot be left behind in these systems in the foam tank and the concentrate lines. It must be removed before fluorine-free foam is put in. The fluorine-free concentrate can only go into a dry tank. In the downstream premix lines, obviously that's less of a problem because it's a premix solution anyway.
Yeah. Very good.
You have another discussion about F3.
Yeah. So Eugene has a very good question. So you treat from Monday to Friday, send the truck off. How do you know there is not rebound? Do we have any data where we came back and checked afterwards, some months later, for instance?
So we have one fire brigade in Germany where we have been periodically testing every quarter for over a year, and to date the results have been fine. We haven't witnessed it on a random sampling from their fleet.
And Greg,
there's a couple of tests. Yeah, there's been a couple studies done in the US, but they're not public yet on rebound. But we have heard through the grapevine that the results look good. There's not a lot of rebound.
Yeah. One of our airport clients.
I guess another point of note, in Germany, they test every year on some of these trucks. And we've been doing this since 2018.
Yeah, one of our airport clients decided on his own to, I think it's every 2 months or so, to go back out and test it. And so far, no bad news.
Yeah.
So that would be a test of whether there was so much PFAS left after our rinsing that it would partition into the new fluorine-free foam, and then you could measure it. But so far, it hasn't caused a problem. And it is, we do treat most systems at least 4 or 5 times, and then flush it all out with water and verify that water contacting all the surfaces hundreds of times, has a very low PFAS concentration of less than typically 1 microgram per liter in the final rinse. So yeah, we're pretty confident of those results. Maybe we'll take one more question, and that is, what guarantees do we offer when we do these cleanouts?
We typically don't offer any guarantees on the domestic side here in the US. I don't know what Cornelison does.
It's kind of reciprocated here, mostly because we don't have control of what that fire truck or system does afterwards and who puts what into it. and we also don't have control of the water. And one point to note is that some of the water that comes into that system while a fire truck may not be PFAS free. Certainly, an example of a fire truck, it could be at a fire and put a pipe into a pond or a lagoon to draw water from. That may have previously been impacted by AFFF. So these things can be easily recontaminated. We've had examples of a fire truck someone put AFFF back into after the fluorine-free was used in it. When they topped it back up, the top up, is still done on a lot of these trucks. So we really lose control. So we issue a document for the status of the truck when it leaves our process. We're happy for that truck to stay out of process for as long as the client require to get the data or to take more data. But once we lose control of it, we can't really guarantee what happens afterwards.
Very good. I think we'll wrap up here. There was another clarification on a previous question. What was the cost range? Someone couldn't hear it. You said 40 to 100K, depending on what type of truck it is and how many you have lined up. And the more you have lined up, the lower the unit cost, right?
Yeah.
And that is typically
kind of based on,
typically 5 to 10% or less of what it costs to buy a replacement vehicle. And even if you did that, you would still have to manage the old contaminated one.
Still that liability. Yeah.
Thank you so much, both of you, for your participation. Thank you, everyone who dialed in, and we hope you liked it. Thank you.
Thank you, Gordon.